Hi everybody, another nodal analysis video. I'm going to do my very best to explain this one. Okay, so on top here is the original circuit. It looks similar to the lab one. As we noticed, and as we know, nodal analysis, we're solving for voltage. So if possible, we need to do a source conversion. And so to do the source conversion, it's voltage divided by resistance to get the current, which is here and here. Okay, once we get the two source conversions, we redraw the circuit, this circuit right here. So we have only one unknown, so we only really need one equation. Remember, when there's one unknown and one equation, you can't put that in the calculator for simultaneous equations. You have to solve it out. So I did the format approach. So I did something, V1 equals the current leaving and entering. So what exactly is touching V1? Well, it's all the resistors. The 2K, the 10K, and the 3.3K ohm resistor. So it's 1 over 2K plus 1 over 10K plus 1 over 3.3K times V1 equals the current. So as you see, we have 3.5 milliamps leaving and 1.2 milliamps entering this node, which is V1. Right here, it would be negative 3.5 milliamps plus 1.2 milliamps gives us a total current of negative 2.3 milliamps. Right here, remember, if a current is leaving the node, so this current is leaving this direction, it would be a negative. If the current is entering the node, it would be positive. So that's how we got this. Okay, so then we write our equation, and we kind of formulate it out. So 1 divided by 2K plus 1 divided by 10K plus 1 divided by 3.3K is 0.903 millisiemens. Remember, when you do the reciprocal of a resistor, that's conductance, and conductance is in Siemens. So now we have 0.903 millisiemens times V1 equals the current. We're trying to solve for V1. So you divide 9.903 millisiemens on this side to get rid of it. We divide 0.903 milliamps here. And remember, current divided by conductance is voltage. So we have now calculated V1 voltage as a negative 2.55 volts. Okay. We bring that back to the original circuit, as you can see. So now this V1 voltage, we know, is negative 2.55 volts. We have to solve for VR1 and VR3. VR2 is just from the node to the reference, so it would be a negative 2.55 volts. Okay, so it's going in that direction, negative, positive. When we calculate for VR1, it's V1 equals VR1 minus 7 volts. And we say it's minus 7 volts because if we go to the node, we pass this, we're entering the negative side of that battery, and then we'd be going down to a node. So it'd be negative 7 volts. So we know that V1 is negative 2.55 volts. So we plug V1 in, we substitute it for what we know. So basically all I did was that, equals VR1 minus 7 volts. We want to solve for VR1, so we have to get it by itself. So we add 7 volts on this side to get rid of it here, and we add 7 volts on this side. So then when you subtract 2.55 and add 7 volts, VR1 is 4.55 volts, and it's a positive voltage. So if you look up here on the circuit from the V1 node to ground, it would be positive and negative because the answer is positive 4.55 volts. So that's how you get the polarity on that resistor. The last one we're going to solve for is VR3. So we're looking at this resistor right here. So we're going to use the same equation, V1 equals VR3 plus 12 volts. And why is it 12 volts? Because from the node down, we hit the positive side of that battery first, and then we get to the node. Same thing like before, we plug in negative 2.55 because that's what V1 is, equals VR3 plus 12 volts. Well, again, we need to solve for VR3. So we subtract 12 on this side to get rid of it here, and we subtract 12 on this side. So VR3 is a negative 14.55 volts. That tells me from the node down, you're going to hit the negative side first and then positive. So it's negative, positive. This is 14.55 volts. VR3, we don't have to calculate at all because from the V1 node to reference, it's the only thing in the path. So that voltage would be negative 2.55, which is why we have negative and positive there. So now what I want you to do, that we have these voltages, is do Kirchhoff's voltage law. The algebraic sum of all the voltage drops around the circuit will give you 0. So I want you to compute around here, you should get 0. Around here, you should get 0. Also around here, you should get 0 because the polarities are correct. Well, I hope this helps. This is solving for one unknown, one equation to get the voltage drops also. See you later. Bye.